Welcome to Learn with Chioma, where we make chemistry simple, engaging, and easy to understand. Congratulations on completing Pack 1, Foundation Guide to Organic Chemistry. In the first pack, we established the foundation of organic chemistry by exploring carbon, functional groups, homologous series, and the basic principles needed to understand organic compounds. Now, we are moving into another important chapter, hydrocarbons and isomerism. Hydrocarbons are among the simplest organic compounds, yet they are responsible for many materials and products we use every day. We will also explore isomerism, a fascinating concept that explains how compounds can have the same molecular formula but different structures and properties. So, prepare your notebook, stay focused, and let's begin this exciting journey.
Before we start learning about hydrocarbons, let's first look at the journey we will take throughout this course.
In this pack, we will begin by understanding hydrocarbons, the simplest organic compounds made from carbon and hydrogen. We will then explore how hydrocarbons are classified and study the major families, alkanes, alkenes, alkynes, and aromatic hydrocarbons. After that, we will enter the fascinating world of isomerism, where you will learn why compounds with the same molecular formula can have different arrangements and properties. Finally, we will strengthen your understanding with revision summaries and examination questions. Now that we know where we are going, let's begin with the foundation of this course. What exactly are hydrocarbons?
Let's begin with the most important question. What exactly are hydrocarbons? Hydrocarbons are organic compounds made up of only two elements, carbon and hydrogen. The word "only" is very important. If a compound contains other elements such as oxygen, nitrogen, or chlorine, it is no longer classified as a hydrocarbon. Although hydrocarbons have a simple composition, they are extremely important because they serve as the foundation for many substances used in our daily lives. Examples of hydrocarbons include methane, ethane, ethene, and ethane. Now that we understand what hydrocarbons are, let's see how chemists classify them. Hydrocarbons are grouped according to the type of bond that exists between their carbon atoms. The first major class is called aliphatic hydrocarbons. This group includes alkanes, alkenes, and alkynes. Alkanes contain only single carbon-carbon bonds, making them saturated hydrocarbons. Alkenes contain at least one double bond, while alkynes contain at least one triple bond. These are known as unsaturated hydrocarbons because they do not contain the maximum possible number of hydrogen atoms. The second major class is aromatic hydrocarbons, which contain one or more benzene rings. Benzene is the simplest and most well-known aromatic hydrocarbon. Understanding this classification is important because the type of bond determines how these compounds behave during chemical reactions. We've classified hydrocarbons into different families, but before studying each family in detail, we need to understand one important distinction: which hydrocarbons are saturated and which are unsaturated. Let's explore that next. Hydrocarbons are divided into two broad categories based on the bonds between their carbon atoms: saturated and unsaturated hydrocarbons. Saturated hydrocarbons contain only single carbon-carbon bonds. Because of this, each carbon atom is bonded to the maximum possible number of hydrogen atoms. The alkane family belongs to this group. Unsaturated hydrocarbons, on the other hand, contain at least one double bond or one triple bond. These multiple bonds reduce the number of hydrogen atoms that can attach to carbon. The double and triple bonds also make these compounds more reactive, allowing them to participate in addition reactions that alkanes cannot easily undergo. A simple way to remember this is, single bonds mean saturation, while double or triple bonds mean unsaturation. Now that we've distinguished between saturated and unsaturated hydrocarbons, let's begin our detailed study of the first and simplest hydrocarbon family, the alkanes. We'll explore their structure, general formula, physical properties, chemical properties, and everyday uses. Our journey into the hydrocarbon families begins with the alkanes, the simplest and most fundamental organic compounds. Alkanes are saturated hydrocarbons because every carbon atom is connected to another carbon atom using only single covalent bonds. As a result, each carbon atom carries the maximum possible number of hydrogen atoms. This is why all alkanes follow a simple general formula: CnH2n+2, where adderizadrond represents the number of carbon atoms. For example, When there is one carbon atom, the compound is methane, CH4. 2 carbon atoms form ethane, C2H6. 3 carbon atoms form propane, C3H8, and the pattern continues. Although alkanes are the least reactive members of the hydrocarbon family, they are among the most important because they are widely used as fuels for cooking, transportation, and electricity generation. Now that we've learned what alkanes are and how to recognize them, the next question is, what makes alkanes unique? Let's explore their physical and chemical properties to understand how they behave and why they're so useful in everyday life. Have you ever wondered why cooking gas cylinders contain propane and butane instead of methane? The answer lies in how easily these gases can be stored. Propane and butane can be converted into liquids simply by applying moderate pressure. This allows a large amount of fuel to fit into a small cylinder, making storage and transportation convenient. Methane, on the other hand, is much harder to liquefy. It usually requires extremely low temperatures or much higher pressures. For this reason, methane is more commonly distributed through pipelines as natural gas rather than stored in standard household LPG cylinders. This is a perfect example of how the physical properties of alkanes influence their everyday applications. Now let's examine the properties that make alkanes so useful in everyday life. We'll begin with their physical properties. Pure alkanes are generally colorless and almost odorless. Depending on the length of their carbon chains, they exist as gases, liquids, or solids at room temperature. The smallest alkanes, such as methane and ethane, are gases. Medium-sized alkanes are liquids and are found in fuels like petrol and kerosene. Larger alkanes become solids and are used in products such as paraffin wax and candles. Another important property is that alkanes do not dissolve in water because they are nonpolar molecules, while water is a polar solvent. This is why oil and water do not mix. Chemically, alkanes are less reactive than alkenes and alkynes because they contain only strong single bonds. However, they burn readily in oxygen, producing carbon dioxide, water, and a large amount of heat. They can also undergo substitution reactions with halogens under suitable conditions. Understanding the properties of alkanes helps us explain why they are so valuable in everyday life. But where exactly do we find these compounds, and how do we use them? In the next lesson, we'll explore the fascinating uses of alkanes, from cooking gas and vehicle fuels to candles, lubricants, and industrial products. Alkanes are not just simple organic compounds, they are essential to modern life. One of their most important uses is as fuels. Methane is the major component of natural gas, while propane and butane are the main components of liquefied petroleum gas, commonly known as LPG, which is widely used for cooking. Larger alkanes are found in petrol and diesel, powering cars, buses, trucks, and generators around the world. Heavy alkanes are also used to manufacture paraffin wax, which is found in candles, crayons, shoe polish, and waterproof coatings. In addition, some heavy alkanes serve as lubricants, reducing friction in engines and industrial machines. Beyond their direct uses, alkanes are valuable raw materials in the chemical industry, where they help produce plastics, detergents, and many other useful products. Every day, whether you cook a meal, travel in a vehicle, or light a candle, you are benefiting from the chemistry of alkanes.
We've explored the simplest hydrocarbon family, the alkanes. But what happens when a carbon-carbon double bond is introduced into the molecule? This small structural change makes a big difference. Let's move on to the next family of hydrocarbons, the alkenes. We've just completed our study of alkanes. Now let's move to another important family known as alkenes. Alkenes are unsaturated hydrocarbons because they contain at least one carbon-carbon double bond. This double bond is the defining feature of every alkene and is responsible for many of their chemical properties. Alkenes follow the general formula CH, which means they contain fewer hydrogen atoms than the corresponding alkenes. Common examples include ethene, propane, butene, and pentane. Because of the double bond, alkenes are more reactive than alkenes and readily undergo addition reactions, making them extremely useful in the chemical industry. The double bond makes alkenes different from alkenes, but how exactly does it affect their behavior? In the next lesson, we'll explore the physical and chemical properties of alkenes and discover why they are more reactive. The presence of a carbon-carbon double bond gives alkenes unique properties. Let's begin with their physical properties. Like alkenes, smaller alkenes such as ethene and propane are gases at room temperature, while larger alkenes are liquids or solids. They are insoluble in water because they are non-polar molecules, but they dissolve readily in many organic solvents. Their boiling points increase as the number of carbon atoms increases. Now, let's examine their chemical properties. The carbon-carbon double bond is highly reactive, making alkenes much more reactive than alkenes. One of the most important reactions of alkenes is the addition reaction, where atoms or groups of atoms add across the double bond. Alkenes also burn in oxygen, producing carbon dioxide and water. Another important chemical test is the bromine water test. When bromine water is added to an alkene, its orange-brown color disappears. This is a simple laboratory test used to identify unsaturated compounds. Now that we've explored the properties of alkenes, let's discover why they are among the most valuable compounds in modern industries. In the next lesson, we'll look at the uses of alkenes and how they help produce plastics, chemicals, and even assist in fruit ripening. Because of their reactive double bond, alkenes are extremely valuable in modern industries. One of their most important uses is in the manufacture of plastics. Ethene undergoes polymerization to produce polyethylene, one of the world's most widely used plastics. Many everyday items, including shopping bags, plastic bottles, food containers, and packaging materials, are made from this material. Alkenes also play an important role in agriculture. Ethene acts as a natural plant hormone that promotes the ripening of fruits. Farmers and food distributors often use it to help fruits ripen uniformly before they reach consumers. In the chemical industry, alkenes are converted into alcohols, detergents, synthetic rubber, and many other useful products. They are also important raw materials in the pharmaceutical industry, where they help produce medicines and medical equipment. These applications demonstrate how a simple carbon-carbon double bond has a significant impact on everyday life. We've explored hydrocarbons with single bonds and double bonds, but what happens when carbon atoms are joined by a triple bond? This leads us to another fascinating hydrocarbon family, the alkynes. Our final major family of aliphatic hydrocarbons is the alkynes. Alkynes are unsaturated hydrocarbons because they contain at least one carbon-carbon triple bond. This triple bond stores more chemical energy than a single or double bond and makes alkynes more reactive in many chemical reactions. Like alkenes, alkynes undergo addition reactions because the triple bond can open up and combine with other atoms or molecules. Alkynes follow the general formula CH. For example, the simplest alkyne is ethene, also known as acetylene, with the molecular formula CH. Ethene is widely used in industries because it burns with an extremely hot flame, making it ideal for welding and cutting metals. Now that we've studied alkenes, alkenes, and alkynes individually, it's time to compare them side by side. This comparison will help you quickly identify their similarities and differences, a skill that's especially useful in WAEC, NECO, and JAMB examinations. Now let's compare the three major families of aliphatic hydrocarbons. Alkenes are saturated hydrocarbons because they contain only single carbon-carbon bonds. They follow the general formula CH and are the least reactive members of the group. Alkenes are unsaturated hydrocarbons containing at least one double bond. Their general formula is CH, and they are more reactive because the double bond can participate in addition reactions. Alkynes also belong to the unsaturated hydrocarbons, but they contain a triple bond and follow the general formula CH. The triple bond makes them highly reactive. Another important difference is the bromine water test. Alkenes and alkynes decolorize bromine water because they contain multiple bonds, while alkenes do not react under normal conditions. If you can compare these three families confidently, you'll find many examination questions much easier to answer. So far, we've studied the three main hydrocarbon families. But there's another unique class of hydrocarbons with a special ring structure and remarkable stability. These are called aromatic hydrocarbons, and we'll explore them next. The final group of hydrocarbons we'll study is the aromatic hydrocarbons. Aromatic hydrocarbons contain one or more benzene rings in their structures. The simplest member of this family is benzene, with the molecular formula CH. Although benzene contains double bonds, its electrons are shared evenly around the ring. This special arrangement, called electron delocalization, makes benzene much more stable than a typical alkene. Because of this stability, aromatic hydrocarbons usually undergo substitution reactions rather than addition reactions. Aromatic compounds are extremely important in industry. They are used to manufacture medicines, dyes, detergents, plastics, solvents, and many other useful products. Understanding aromatic hydrocarbons completes our study of the major families of hydrocarbons. We've now completed our study of the major hydrocarbon families. The next concept explains something truly fascinating: how compounds can have the same molecular formula but different structures. This phenomenon is called isomerism, and it's one of the most important topics in organic chemistry. We've successfully explored the major families of hydrocarbons. Now, let's move into one of the most interesting topics in organic chemistry, isomerism. This concept explains how compounds can have the same molecular formula yet behave differently because of how their atoms are arranged. Now let's explore one of the most fascinating ideas in organic chemistry. Sometimes, two compounds can have exactly the same molecular formula, yet they are not the same compound. How is that possible? The answer is isomerism. Isomerism occurs when compounds contain the same number of carbon and hydrogen atoms but differ in the way those atoms are connected or arranged. These compounds are known as isomers. A good example is CH. This molecular formula represents both butane and 2-methylpropane. Although they contain the same atoms, their structures are different, giving them different physical properties. Understanding isomerism is essential because it helps explain why compounds with the same formula can behave differently in chemical reactions and in everyday applications. Now that we understand what isomerism means, the next question is, are all isomers the same? The answer is no. Isomerism is divided into different types, each based on how the molecules differ. Let's explore the major types of isomerism.
Butane, C4H10. It splits into chain isomers. Let's examine the types of isomerism.
Now that we understand what isomerism is, let's look at its different types. Isomerism is broadly divided into two categories. The first is structural isomerism, where compounds have the same molecular formula but differ in the way their atoms are connected. Structural isomerism includes chain isomerism, position isomerism, and functional group isomerism. The second category is stereoisomerism. Here, the atoms are connected in the same order, but they differ in their three-dimensional arrangements. One important type of stereoisomerism at this level is geometrical isomerism, also known as cis-trans isomerism. In the next few slides, we'll examine each type one by one using simple structural diagrams. Let's begin with the simplest type, chain isomerism. We'll learn how the same molecular formula can produce different carbon skeletons. Changing the carbon skeleton gives us chain isomers. But what if the carbon chain stays the same and only the position of a double bond or functional group changes? That leads us to another important type of isomerism known as position isomerism. Let's move to the second type of structural isomerism, position isomerism. Unlike chain isomerism, the carbon chain does not change. Instead, the position of a double bond, triple bond, or functional group changes. Consider both 1Na and both 2Na. Both compounds have the same molecular formula, tetracarbon octahydride, and both have 4 carbon atoms arranged in the same chain. The only difference is the location of the carbon-carbon double bond. In both 1Na, the double bond starts at the first carbon atom, while in both 2Na, it starts at the second carbon atom. Because only the position changes, these compounds are called position isomers. We've seen how changing the carbon chain gives chain isomers, and how changing the position of a bond gives position isomers. But what happens when the functional group itself changes while the molecular formula remains the same? Let's explore functional group isomerism. Let's look at another fascinating type of structural isomerism called functional group isomerism. In this type of isomerism, the compounds have the same molecular formula, but they contain different functional groups. Consider ethanol and dimethyl ether. Both have the molecular formula CHO. Ethanol contains the hydroxyl group, making it an alcohol. Dimethyl ether contains an oxygen atom linking to carbon groups, making it an ether. Although they contain the same numbers of carbon, hydrogen, and oxygen atoms, they belong to different classes of compounds and therefore show different chemical properties. This is why identifying the functional group is very important in organic chemistry. We've now explored the three major types of structural isomerism. The final type we'll study is geometrical isomerism, where molecules have the same structural formula but differ in their arrangement in space around a double bond. The final type of isomerism we'll study is geometrical isomerism, also known as cis-trans isomerism. Unlike structural isomerism, the atoms are connected in the same order. The difference lies in how they are arranged in space around a carbon-carbon double bond. The double bond prevents free rotation, so the groups attached to the carbon atoms remain fixed in position. When similar groups are on the same side of the double bond, the compound is called the cis isomer. When they are on opposite sides, it is called the trans isomer. Although cis and trans isomers have the same molecular formula and structural formula, their different shapes can lead to different physical properties, such as melting and boiling points. Congratulations! We've now covered all the major types of isomerism. The next step is to apply what we've learned by solving worked examples similar to those found in WAEC, NECO, and JAMB examinations. Let's put everything we've learned into practice with some exam-style questions. Whenever you're answering organic chemistry questions, don't rush. First, identify the molecular formula or the type of bond present. Next, compare what you see with the rules you've learned. For example, if you see the formula CH, you should immediately think of alkanes. If bromine water is decolorized, think of an unsaturated hydrocarbon such as an alkene. If the carbon skeleton changes, it's chain isomerism, while a change in the position of the double bond indicates position isomerism. By following these simple steps, you'll answer exam questions more accurately and confidently. Congratulations! You've completed hydrocarbons and isomerism. Before your examination, make sure you remember these key points. Alkanes follow the general formula CH and contain only single bonds. Alkenes have the formula CH and contain at least one carbon-carbon double bond, while Alkynes follow CH and contain a carbon-carbon triple bond. Remember this simple rule: longest chain first, then name the compound. This single principle will help you avoid many common IUPAC naming errors. Also revise the three major reactions. Combustion produces carbon dioxide and water. Addition reactions are typical of alkenes and alkynes, while substitution reactions are characteristic of alkenes. Finally, watch out for common examiner traps. Never count every carbon atom when identifying the parent chain, always number correctly, and don't confuse the suffixes N, Ne, and in. If you master these concepts and practice past WAEC, NECO, and JAMB questions, you'll be well prepared for your examination.